Okay, let's now look at one of the most important redox schemes used by chemists every day. You'll be using this quite a lot in organic too also. A redox scheme which changes various functional groups into other functional groups. Now when we're looking at our general scheme here, two things to note. Going from an alkane to an alcohol is actually, as we've said before, not the easiest thing to do. Hopefully by the end of the semester, after chapter 15 radical reactions, you'll be able to see how that can be accomplished, but that's not that commonly done. Turns out, taking any of these molecules, going from an alkane, alcohol, ketone, aldehyde, carboxylic acid, and converting it to carbon dioxide is extremely easy to do. You just light it on fire. But then that creates our problem. If you had such a strong oxidizing agent, or if you light it on fire, any of these just immediately form carbon dioxide, a combustion reaction. The big trick is, how do you go from alcohols to aldehydes to carboxylic acids and back? What 8 reagents will do these oxidations and reductions without forming carbon dioxide? So that is this general scheme here, that it's a really good idea just to memorize this. It's going to be a little complicated, well, not too complicated, but a lot of memorization here. All right, so here we go. Here, let's start by looking at, we have primary alcohol in this box, such as ethanol, the aldehyde here, and the carboxylic acid in this box. Now, if you want to go from a primary alcohol and oxidize it all the way up to a carboxylic acid, that's actually not too hard to do. You just use one of our strong oxidizing agents. Potassium dichromate, potassium chromate. Recall those have chromium in the +6 oxidation state. Potassium permanganate, manganese in the +7 oxidation state. All nice, good, strong oxidizing agents. They will take a primary alcohol and oxidize it 2 steps all the way up to the carboxylic acid. But say you don't want the carboxylic acid, say you've got your primary alcohol and you just want the aldehyde. Well, that can be done, but you need a milder oxidizing agent. And our mild oxidizing agent is PCC. And PCC, I'll show you the structure down here, stands for pyridinium chlorochromate. A pyridine, which is like a benzene ring, only there's a nitrogen in it, adds a hydrogen, makes it positive charged. And this is like chromate, but chromate is CrO4 minus. We've added a Cl there, took away one of the oxygens, so it's pyridinium chlorochromate. But everyone just calls it PCC. It is a milder oxidizing agent and will get the job done. Anything stronger than PCC will take the primary alcohol to the carboxylic acid. All right, so you have your aldehyde. Well, if you have your aldehyde, you want to oxidize it to a carboxylic acid. No problem, just add one of these strong oxidizing agents. Yeah. Potassium dichromate, etc., any of these guys will take that aldehyde and oxidize it to the carboxylic acid. All right, so what if you have a carboxylic acid and you want to reduce it down to a primary alcohol? There's only one real good reagent for this, one main way of doing that. That's with lithium aluminum hydride, LAH. Now, lithium aluminum hydride is nice. It is a very strong reducing agent, but it is nasty. It is a very strong reducing agent. It is actually quite dangerous. Lithium aluminum hydride, if you accidentally pour some water on it, it will explode, and there goes your hand. So it's quite the dangerous reagent, but it does a very good job of converting a carboxylic acid to a primary alcohol. That will work. What if you have an aldehyde and you want to reduce it to the primary alcohol? You've got 2 choices. You could use lithium aluminum hydride, because that's really nice, that'll work, or sodium borohydride. Now, the most obvious choice here is sodium borohydride. It is much less nasty. It is not nearly as dangerous as lithium aluminum hydride is. If you have an aldehyde and you want to reduce it to a primary alcohol, using lithium aluminum hydride is just super overkill. It's just not necessary. Sodium borohydride is so safe, in fact, that we used it. Yeah. When we did the chromatography lab, when we took fluorinone, the ketone, and reduced it to fluorinol, the alcohol, we used sodium borohydride. So it's much more common reagent. You'll find that much more commonly in the labs because it will do this reaction very nicely. Lithium aluminum hydride just too nasty. It'll do it, but it's just a very, very powerful reagent. So note here we've got a little space. What if you have a carboxylic acid and you want to convert it to the aldehyde? The answer is, in one step, there is no reagent that'll just do it. That just doesn't happen. Now you're saying to me, but wait a minute, I have a carboxylic acid right over here, and I want to turn it into an aldehyde. How do I do that? Well, you look at this chart here, and you tell me, if you have a carboxylic acid, how do you change it to the aldehyde? Yeah, it doesn't take very much logic to see, okay, I get some very dangerous lithium aluminum hydride, reduce the carboxylic acid to the primary alcohol, and then add PCC to oxidize that alcohol to the aldehyde. That's the only way we can do it so far. When you take organic 2, we will show another way to take a carboxylic acid and convert it to the aldehyde, but it's not a one-step reaction. It's not one reagent that'll do it. Again, it's 2 reagents that are necessary. All right, and our last part down here, very similar. What if we have a secondary alcohol and want to convert it to a ketone? Truthfully, people have a lot of PCC lying around because they're oxidizing their primary alcohols to aldehyde, so the best way is just use our mild PCC pyridinium chlorochromate reagent to oxidize the secondary alcohol into the ketone. However, you don't have to. You could use the potassium dichromate. You can use some of those strong oxidizing agents. They will do the job also. What you see here, or what I hope you are sensing, is that ketones are pretty stable and it's difficult to oxidize a ketone. Yes, recall that oxidation is adding CZ bonds or the removal of carbon-hydrogen bonds, taking away hydrogen. Aldehyde has a hydrogen you can take away. Ketone, there's not a hydrogen on this carbon to take away. Therefore, oxidizing a ketone is pretty hard. Now, you can do it. Heck, this is acetone. Light it on fire. You could oxidize it all the way to carbon dioxide, but that's not what you want to do. So oxidizing this to something other than carbon dioxide, oxidizing it to a carboxylic acid or an ester or something like that, is actually quite difficult with a ketone. But say you have your ketone and you want to reduce it to the secondary alcohol, best way, sodium borohydride. That's what we did in lab. It's much safer. The reaction works really well. Yes, you could use lithium aluminum hydride if you wanted to, but that's a bit of an overkill and it's much more dangerous. So these 2 schemes here with our primary alcohol to aldehyde to carboxylic acid, secondary alcohol to ketone, extremely important. When you take organic 2, you're going to be using these reactions all the time because we've already looked at the reactions of primary and secondary alcohols and what we can do with them. In organic 2, we're going to look at ketones, aldehydes, and carboxylic acids and look at their reactions. So being able to take an alcohol and convert it into a carbonyl then opens up a whole area of carbonyl chemistry that you can do to make new molecules. So, very important steps. I'm going to keep this video kind of short to just look at that because this is very important. You need to know this.